Hello everyone. In this video, we're going to be talking about the actual algorithms and implementations of Prim's minimum spanning tree algorithm. We're going to analyze a bit of the runtime while going through this, and we're going to understand whether or not these algorithms are correct and maybe some smart ways of implementing them. So here's the sort of absolutely basic version of Prim's algorithm. What we're going to do is we're going to, given a graph, which we will draw down here, some graph with various edges and vertices, and some weights on those edges. 1, 2, 4, 4, 8, 3, 9, 8, 2, 1, 6, 11, and 4. We have some graph with various weights associated with the edges. We're going to choose one of them to start at. In this case, we call it V1, just any vertex. If you were coding this yourself, you might make that an arbitrary choice, or it could just be the first thing in the adjacency list. So we choose some starting vertex V1. That is going to be the root of our minimum spanning tree. So that's what the first couple of lines there do. This set U, if you remember when we first introduced the algorithm, we colored nodes orange once we discovered them. The set U is the set that contains all those white nodes that we have yet to add to the spanning tree. So while there are still nodes to add, that's while U is not empty, and while there is an edge from the orange things to the white things, it's possible they have a disconnected graph, in which case asking about the minimum spanning tree might be a slightly awkward question. So that last case is to guarantee when you have a disconnected graph, that you still get some answer out of the algorithm. So while we still have vertices to add, and we can add those vertices, we're going to do something. What are we going to do? Well, we're going to pick the minimum weight edge, the greedy decision, from the orange to the white. So here, the edge I would choose would be the edge there that has a weight of 1, and then I would add this node, let's call it V2 because we haven't named them yet, and set its parent to be V1. So some way we designate that it has a parent in this minimum spanning tree. So that is what we're going to do. We repeat this until we've created the entire minimum spanning tree. So just for completeness' sake, we need to add in the next smallest edge, which would be this guy. We then need to add in the next smallest edge, which would be that guy. Then the next smallest edge, which would be that guy. Oh, oops, I lied. Let me undo. The next smallest edge is the 2. Oh, sorry, this is the... I don't think I assigned a weight to that edge. Let's make it 8 or 7. This is the next smallest. That's the next smallest. And then we have a 8 going here, a 6 going there. So a 6 going there seems like the right choice. And then up there. We color all of them orange. So that's walking through the algorithm there. All of them are connected now. That's our minimum spanning tree. So this seems like a very straightforward algorithm. It's just do the stuff we said. How long does it take? That's the obvious question to ask. We know it's correct because of our proof we did of the minimum spanning tree theorem. So it's guaranteed to be correct. We just need to know the running time. So step 1 is how many times does this line run? Line 4, the while loop. Well, the while loop is going to execute for every single vertex. So it's going to run n times if n is the number of vertices. And if we let m be the number of edges, that might show up as well. The next line is a very cheating. So 2 of these lines are really easy. This line here of assigning the parent, and this line here of assigning removing VJ. Those both take constant time. The real trick here is going to be finding the minimum weight edge from one to the other. The problem is we're going to have to actually check almost all of the edges because we are going to run through every single vertex. So this actually is less than or equal to c times m, and it turns out that's a type bound. We aren't going to bother proving that, but we could if we wanted. So this version, line 4 runs n times, and line 5 runs less than or equal to m times per iteration. That gives us that T of n is in big O of n times m, which it turns out it's in theta of that, but we're not actually going to care too much because it turns out this is not a great algorithm. Why is it not great? It's because no matter what, this runtime can't be very good. So, what do we know about m? What do we know about m? Can we bound it? Less than or equal to, greater than or equal to. So what's the minimum number of edges, m, we can have, and what's the maximum number of edges we can have? If you remember, the minimum number of edges is the number of edges in a tree. The smallest graph we could have that has a minimum spanning tree would be a graph with n minus 1 edges. It would already be a tree. This is that your graph G is a tree. The alternative, the absolute most we could have, is n times n minus 1 over 2, which you might remember as G is a complete graph. So we're bounded between these. So m is somewhere between n and n squared, which means that Tn could, in the worst case, be in big O of n cubed, which, and even in the best case, the absolute best case where we just have a tree, we would have to be at least in big O of n squared. There's no way around that. That's already not a great runtime. Big O of n cubed is actually somewhat catastrophic for reasonable graphs, which reasonable graphs can turn out to be 10 million edges, 100 million edges, 10 billion edges. These things can become gigantic. And those things having a cubic runtime turns out to be very, very, very bad for those algorithms. So this means that this isn't great. So we need to improve. So let's find out how we can do that. Let's draw a graph. We have some graph here. With edges, and there are weights associated with those edges. Let's say we have 7, 8, 2, 9, 11, 6, 8, 4, 9, 4, 10, and 2. So we have some edges that have weights, and now what we're going to do is actually add in a bit of extra information to try and make this more efficient. What we're doing, the reason the last algorithm turned out to be very bad is that we keep rechecking edges we've already checked before. So if we scroll up, looking at this, until I added in, let's call it V3, every single iteration of the loop, I'm going to be checking, is that edge 8 the one I'm going to take? Is that edge 8 the one I'm going to take? Is that edge 8 the one I'm going to take? Which is not great. So we're going to get around this by storing some of that information that we're processing every single time. So what we're going to do is store a cost at each vertex. We're going to initialize this by saying the cost at the starting vertex is 0 and everywhere else is infinity. This blue thing corresponds to a cost of adding the node. So the blue equals cost of adding vertex. What I mean by that is that what is the cost of the edge I'm going to use to add that vertex to the tree? We're then going to look across all of the white vertices and say, what is the cheapest one? The cheapest one here is pretty obvious. 0, last time I checked, was less than infinity. So we're going to choose 0 to add to the graph. So once we've added that, we're going to look over every single one of its edges and update the cost of adding those nodes. So I'm going to update the cost of the 2 adjacent nodes here. The top node has a cost of 7, because I could add it using that edge 7. And the bottom one has a cost of 8, because I could add it using that cost 8. And what I'm going to store is how does it cost that much. So it costs that much by, oops, undo. It costs that much by using that edge there. And this one costs that much by adding that edge there. The green is what we're going to call the parent. And it's a temporary idea of what we had above up here. That blue line we used above. Now, we're going to look across all of the white nodes and say which of those costs the least. The least of them now is going to be that one that has a cost of 7. And then we add that in. Let's shade in that line. So we add that one to the graph. Now, I need to update the cost of every single node adjacent to the one I just added. Notice I never need to look back at the first node ever again, because I've already assessed how good are the things next to it. So I need to look at 3 nodes here. I need to look at the node below it, which has a better cost if I was to use this edge. The cost now for that vertex down there is going to be 2. And I'm going to delete that parent that I had before. And for the 2 nodes that have an infinite cost, I'm going to update those to 11 and update this one to 9 and update the corresponding parents. Now add the minimum weight edge and add that vertex to the graph and then update all the things adjacent to it. I found a new node over here that I now update its cost from infinity to 6. And I find a new node. I find this node up here and update its cost to be 4 and change its parentage. Now I look at the minimum cost node of the white nodes. We have 9, 4, 6, and infinity, infinity. The best of those is 4. Oops, undo. The best of those is 4. And then I look at everything adjacent to that. All of the white nodes adjacent. So I would check, okay, I already have that one added. This one down here, I have a cost of 9. I don't update that 6 because 9 is a worse cost. And I go up here, that one is a cost of 4, but I had a cost of infinity. So I update that infinity to be 4. I then add this one to the graph. And now I'm going to look at all of the white vertices and see which one's the best. We have 9, 4, 6, and infinity. Winner of that one is 4. And then we add it to the graph. I then update everything adjacent to it. Update 9 to be 8, and its parent gets updated to be the parent of, to be 4, that node that had a cost of 4. Now we check what's the and I also find this one over here, which now has a cost of 10. I now look for the minimum edge. I have 8, 6, and 10. Winner of that bout is 6. So I add it using the path that had the parent. Add it to the graph. Update everything adjacent. I already have this one added. I need to update here. Oops, sorry. Undo. Undo. Need to update this one to be 2. Add the minimum weight edge. Minimum weight edge is 2 now. Add it to the graph. And then I only have one white vertex left, and its cost is going to be 8. So I add it using the correct edge. So we are going to store this cost, and this way all we ever need to look at for determining what node to add is going to be the nodes. We never need to look at the edges again. We're going to process through each node. The reason that the inefficiency was coming is that we were looking at tons of erroneous edges before. So let's check how it's implemented. It's going to look much messier, we'll see here. So it takes almost the entire screen. Let's process what this code does. U, as before, represents the white vertices, the ones we have not added to the tree. We're going to start by initializing the problem. Every single vertex gets a cost of infinity. So we start by initializing by setting everything to be infinity. And then that first node gets a cost of 0 and has no parent because it's going to be the root of our tree. Then, while there are still nodes to be added, and there is something that has a cost less than infinity, so it's still reachable. If every single node had a cost of infinity, then nothing is reachable via this algorithm. So if we had a disconnected graph, the way we're going to say it's disconnected here is if there's a cost of infinity and no more new nodes to add as a result. So we're going to choose v sub j, just like we did last time, as the one that has the minimum cost. But we're going to choose it like we needed to last time, but this time it's the one that has the minimum cost. So we're going to iterate over all of the vertices and find the one with the minimum cost. Then we're going to set the parent in the minimum spanning tree, a different parent than we had before, to be the parent of v sub j. What does that mean? That means that we are adding via the green lines we used above. So that is what we're representing there. The green lines, the green arrows, correspond to the parent. The green highlighted lines correspond to MST parent. So we add it to the graph. So this part here, add it to the tree. This is add to MST. And this line up here, undo, is make the greedy choice. Be greedy. So the one downside here is that now we need to update all of the things that were adjacent to the node we just added. So this is for every vertex adjacent to v sub j. So all adjacent vertices. ADJ for adjacent. I'm just going to say nodes because it's easier. So for all adjacent nodes, if the cost from this new vertex we just added, if the cost from the new vertex, the weight of that edge, v sub j to v sub k, is less than the cost, if it's cheaper to use this new edge we just discovered, then we're going to use that edge. So if the adjacent thing is in U, if it's a white node, and it's cheaper to use this new method, then we update the cost and the parent. That's where we crossed things out in blue and updated the green arrows. So how long is this going to take? Did this actually buy us any efficiency in the algorithm? Let's see. So line 8 will always run n times. There's no way around that. This code up top is going to run in Cn. So that's not bad. The setup didn't cost us too much. So what is the cost of looking at each of these nodes? If we wanted to be precise, maybe we would write this as, at the start, we would have every node, it would be n for the first run, and then n minus 1, and then n minus 2, and then we would keep going. This would be n minus I after we've added I vertices. So that it's going to check over every single vertex in U, which is all, if we're imagining the graph is connected, is going to be all of the vertices that haven't been added. So it's going to be n at the start, because we haven't added any vertices, then n minus 1, because we've added 1, then added 2, then added 3, and so on. So that part's not too bad, hopefully. Now, let us check out this part here. You might remember that if you're checking all of... Oh, sorry, let's do this a different color. If you're checking all of the vertices adjacent to a particular vertex, all of the edges that are incident, that is the degree of the vertex. So this runs in time degree of the vertex we're processing all of the edges for, which is v sub j. Maybe if I want to be more precise here, what I would do is actually use a j up here. But we're not really going to write these as summation, so it's okay. So let's process this. So line 9 and then lines 12 through 17. So line 9 takes n plus, runs. I used purple. N plus n minus 1 plus n minus 2 plus n minus 3 plus all the way down till 1. And if we remember our formulas, we know that that is equal to n times n plus 1 over 2. So that's not too bad. This was line 9. Then lines 12 through 17 run the sum from j equals 1 to n. For every single vertex, we're going to run through the degree of v sub j. No matter what. So, if we are adding up, for one run it takes the degree, and we're going to add that up over every single vertex as we're adding them. So, if we remember, that takes that would run 2m times, where m is the number of edges. If you add up the degree of every vertex, you're looking at each edge twice. Once for the first edge, where you're leaving it, and then once for another edge where you're going back to it. So, the total runtime, t of n, is in theta of, line 9 takes n squared time, and then those other lines take m time. And depending on the graph, m has certain variability. M goes, again, from about n minus 1 to about n squared over 2. So this is going to be in theta of n squared, or big O of n squared, guaranteed. So this is guaranteed to be roughly better than the last one. In very particular cases with a very tree-like graph, it can actually turn out that this one is slightly less efficient because of the overhead of all of the setup. But for most practical problems, this is going to be a preferable algorithm. But can we do better? Why and how could we do better? The primary problem here is coming from having to look through all of these edges. We're trying to find a minimum. And the minimum was taking us linear time, n minus 1. And finding minimums in quick time, we actually have a convenient data structure for that. So our idea, to make this more efficient, is use a priority queue. This was a really good data structure when you needed to keep finding the minimum of something. In fact, we're going to use a priority queue, but we're going to use a slightly different version than we've talked about before. We're going to use what's called a min heap. A min heap, to be precise. Before we used a max heap, this is the exact same thing, but we have a minimum at the top instead of a maximum. So, we have some methods we're going to need. We're going to have insert, extract min, determining the min, and what's going to be called decrease key. So, insert, if we remember, took log s time, where s was the size of the data structure. Extract min took log s time. That removed the minimum and then fixed the heap. Minimum is just finding the minimum. That's guaranteed to be the root. That's going to take constant time. And decrease key will take some node in the heap and change its value downwards. By doing this, we break the heap structure and might have to fix it, so it takes log s time, where s is the size of the priority queue. So, rather than storing the vertices as this sort of set that we have to iterate over all of the vertices, what we're going to do instead is going to use a priority queue and then use that to store those minimums, the minimum costs. So that is all we're going to change. The previous code, we stored these costs and accessed them by sort of iterating over every single vertex. There's no need to do that when all we need is the minimum every time. So this code will look a bit messier because we're using data structures. I actually think it looks a little bit nicer because it looks more like how I would actually code it myself. Because I know even if I was to code it like what we have up here, it would have less math in it. The one we're going to have is going to have less math in it and therefore look more like what you're expecting from Java or C++ or Python or something like that. So here we have our alternative version using a priority queue. Step 1, initialize the priority queue. So we initialize the priority queue. We then are going to use the queue to store the vertex and its cost. You could argue, well, how are you sorting it? We'd have to implement this queue a little bit particularly, where we are iterating over the queue and determining the minimum by looking at the cost, but we're also storing the vertex. A bit of details there, it doesn't matter too much, so we're going to mostly ignore it. So we're going to insert into the queue every single vertex and its associated cost. So we insert every single vertex into the queue, and then we're going to insert the one we didn't, v1, at the end. And then we're going to keep iterating while there are things in the queue to be processed. This queue now represents the nodes we need to add. We're throwing them all in a queue, and then we're going to add them as we go. So while the queue isn't empty, and the minimum node isn't infinitely far away, we're going to find the minimum. So while there are nodes to be found, we get the minimum from the queue and add it. So this is find best node, find best, and add it. Okay, and then we're going to do the exact same thing we did last time, where we are going to, for each edge that is incident, if the queue has that edge, so if it's a white node, that's what the queue.contains does, that would take log s time. So I guess I didn't mention that method, so I apologize. So if it contains it, and the weight from this new vertex is less than the current weight, so if it's better to use this new vertex, then decrease the key and fix it. So how long is this going to take? This code here takes log of s times the degree of the vertex. Because the log of s comes from the queue, and we need to do this for every single vertex adjacent to vj, so we get the degree out of it. So the c times log of s is the cost of doing the contains, the decrease key, and the key operations. Each of those takes log of s time. And the degree of vj, we need to do that for everything adjacent to vj. The green code is just going to take log of s time. So let's look at what's happening here. Line 9 and 10. So I'll just call it line 9. Takes log of 1 plus log of 2 plus up through log of n time. And we've done this infinitely many times by now between foundations 1 and foundations 2. That is in n log n. Lines, let's make sure we get the numbers right, 11 through 16. Take the sum from j equals 1 to n of c log of s times the degree of v sub j. We could factor out the c log of s, and then we add up the degree of every single vertex, which we've seen before, is going to be 2 times m. So this equals 2 times m times c log of s. So t of n in this case is in theta of n log n from line 9 there plus m log n Sorry, this should be log n just to make our lives easier. For the second sum. Let's make it log n here as well. Knowing this runtime is going to definitely be better than the last one. The last one was n squared plus m. So we lose a little bit in the second term, but save a lot in the first term. N squared is substantially worse than n log n. So we make some savings here by using a data structure. As we've seen before, we always pay a bit of a price. The first algorithm was n cubed, but didn't have the number of vertices in it anywhere. This algorithm the second algorithm, was an n squared plus m. We paid a cost by adding in the number of vertices as a trailing term. We then made that cost worse by adding in a log n factor to it as well here, but we improved the bad term. As we've seen several times, by using better data structures, you can improve the runtime of one part of the code while paying a price in another part of the code, which is what we've done here. So by paying a price in terms of updating everything in the queue, that's this m log n term, we've improved the efficiency of the algorithm in the first part. I'm not going to ask you to replicate the method we did here, but you should definitely understand it and should be able to do sort of similar analysis at some point. Importantly, at least understanding roughly how to do this is important. I might ask you, for example, to verify or for certain parts of this as a problem. The important part for applying the algorithm is that these second two methods are monstrously tedious, as we saw when we ran through this cost example. If you're going to actually run this algorithm by hand on any example I give you, I would strongly recommend using the first algorithm. That's the much more humanly usable algorithm. But for the computer, when you're having large numbers of nodes and vertices, in the millions or billions, it's going to be much more efficient to use those second two algorithms over the first one. So, this is the last thing we need to mention with prims. We start with an algorithm, the very naive implementation. We fix it by thinking cleverly about reducing the workload a little bit. And then we improve that one by using a data structure to make the code more efficient, which is this third implementation. And that is pretty much the last thing we need to do for minimum spanning tree.